Hello everybody, welcome to my talk about extracting insights from the vector space and automatic ontology construction from text data. The work that I will present here is inspired by client projects that we do at my company Anacode, and this is why I would like to start by presenting the business challenge that we are solving. Then in the second step, I will present the NLP task that we use to tackle this challenge, and specifically it's the task of automatically constructing ontologies, and even more specifically the task of learning lexical relations such as hyperenemy from our text data. And finally, I will present our approach to this task. So first, for the business challenge. In general, what we do at Anacode is market intelligence for companies based on online data and specifically text data from the web. So this can be different kinds of data. Obviously, we use a lot of social media, but then also other data types such as business press, general press, specialized press, and also more technical publications such as patents and scientific papers. And in the last 2 years, we have more and more clients coming to us with challenges and questions about new technologies and specifically about how they can discover and analyze new technologies based on all the web data that's out there. So we all know that we live in a world which is developing very quickly and also changing very quickly. And for businesses, it's becoming more and more challenging to actually keep up with all these changes and developments. So the data set that we use to solve this task is obviously very dynamic. It's also changing very quickly, and so is the conceptual framework that we use that we basically use as a framework to answer our clients' questions. So just as an example, what are some questions that can be raised and can be answered? These are questions from different departments. So, for instance, from strategy and planning, the classical question is, what are the new trends and technological developments in my domain? There are also a lot of questions from competitive intelligence, because obviously a lot of it is related to observing and monitoring competitors and understanding and anticipating what they're doing, and also kind of trying to learn from what the competitors are doing. So here a classical question is, are there any new substitutes emerging from my product? There are also a lot of questions about leapfrogging and other competitive strategies. Um, Then we have questions from other departments like investment, like procurement, marketing, and so on. So you can see that these questions are very diverse, and the framework has to be flexible enough to accommodate all these different types of information. That's one thing. That's one requirement for our conceptual framework, and obviously the second requirement also is that it has to be very dynamic and adaptive and able to learn from new incoming data. What do we use as our conceptual framework? We use actually quite an old school concept, and specifically the ontology. So as most of you might know, ontologies are classifications of knowledge with some relationships that can be established between the different classes and the different instances in the ontology. So on this slide, you can see, just to illustrate, a very small excerpt of an ontology for the cybersecurity domain. So in cybersecurity, the cyber attack is a very central concept, and you can see that we subclassify cyber attack into different, more granular types of attack, such as the network attack, the botnet attack, and then even more granular attacks like man-in-the-middle attack, denial of service, and so on. This ontology is created for cybersecurity, and actually many of the examples that I will present in the following slide, they are also focused on cybersecurity. As said, this is actually inspired by a real life project, but as you can imagine, different clients can have questions from different technology corners, and even the same client might actually face challenges both in cybersecurity and artificial intelligence, and maybe even things like quantum computing and so on. So actually our framework needs also to be able to learn these classifications for different domains, because it's not realistic to maintain an ontology like this in a manual way. Good. So now coming to the natural language processing task of hyperenemy discovery, let me first introduce what hyperenemy is. So hyperenemy is a lexical relation along with other relations such as synonymy, meronymy, and so on, which does signal some kind of logical relationship between two words or two concepts. And so actually do the other lexical relations. So synonymy is also a kind of a similarity or identity relationship. Meronymy is a part of relationship, and so on. So these are all relations which are actually very important to learn conceptual knowledge from data. Specifically, hyperenemy means that, so if we have a hyperenemy pair x and y, then we can say that x is a kind of y, and in that case we also say that y is the hyperonym of x, while x is the hyponym of y. And you can see on the slide the notation that I will also use in the following explanations. Hyperonymy can apply to different parts of speech. So obviously the classical example is nominal hyperonymy. For instance, penguin is a kind of a bird, war is a kind of a conflict, and so on. But it can also apply to other parts of speech like verbs, so walking is a kind of moving, and adjectives like petite is a kind of small and wine is a kind of red. Note in the last example, wine is a kind of red only when wine is used in the sense of the color and not the beverage. So important note, hyperonymy applies at the sense level, not the word level, and this obviously offers additional potential to a more granular approach on the side of NLP. The logical relations of hyperonymy are transitivity. So if x is a hyponym of y and y is a hyponym of z, then we can also follow that x is a hyponym of z. And asymmetricity. If x is a hyponym of y, then y is definitely not a hyponym of x. This is quite logical because we have seen that the hyponym is more specific, so one term cannot be more specific and more general than the other at the same time. In the following, we will not really go into the transitivity relation, but we will talk quite a bit about the asymmetricity relation, because this is something that can be learned from linguistic data, and this is something that allows us to determine the directionality in a specific candidate hyperonymy pair. Now, what are the linguistic properties? There are three properties. There are certainly more, but I will focus on these three because actually these are also the three properties that we're using in our own approach to gradually build up our system for hyperonymy discovery. So the first property is that hyperonyms and hyponyms tend to co-occur in phrases or sentences or quite, like, let's say, small linguistic context. And even more specifically, they tend to co-occur in specific lexicosyntactic constructions or patterns, such as x, such as y, x especially y, y and other x, and also nominal collocations. And this is something that can be very nicely used, as you can imagine, for a pattern-based bootstrapping and basically based on syntactic rules. Then the second property, distributional similarity. I'm sure that most of you know what distributional similarity is, because it's the underlying principle behind the word vectors and the word embeddings. So basically, distributional similarity tells us that words that are semantically similar tend to occur in similar contexts. If we have a context like engine and we know that it can co-occur with automobile very naturally, then we can as well look at the hyponyms of automobiles such as SUV, such as electric car, and we can predict with a very high probability that these words are actually also likely to occur in the context of engine. So third property is asymmetry. So far, so especially for a distributional similarity, we're on the symmetric side, because when one item is similar to the second item, then it means that the second item is also similar to the first item. This is not what we want in the end for hyperenemy, and thus we need to bring in the asymmetry. And we do this by considering the specificity of the context in which hyponyms versus hyperonyms occur. And here, the observation that we make is that hyponyms can occur in more specific contexts that are not shared by their hyperonyms. So we can say the dog is barking, but once we replace the dog with its hyperonym, animal, then the animal is barking does not work anymore, because apparently every hyponym of animal actually has its own way of making sounds. That would be the hyperonym in this case, basically for the verb. Okay, so now our own approach. Let me first say some words about our data set. The data corpus that we use is actually quite small but very clean. So we use 10 million English sentences which were extracted from around 20 websites focused on technology and business, such as TechCrunch, The Verge, VentureBeat, also more scientific publications like Science Daily, Nature, and so on. And what are the characteristics of this data? As said, it's clean, which is quite pleasant, so it's professional writing which is edited, and it's also quite focused, because obviously a requirement for a good text is always that it's focused on a specific question or a specific issue. It is a mix of content on technology and business, and as you can imagine, so I said at the beginning that all this data is changing very quickly, so there are many named entities and also many unknown out of vocabulary named entities, and also many multi-word expressions which are actually a challenge in themselves. Now, our approach comes in a pre-processing step and then 3 additional steps which follow exactly those 3 properties, 3 linguistic properties of hyperenemy that I outlined before. So after the pre-processing, we apply rule-based bootstrapping to capture the tendency of hyponyms to co-occur with their hyperonyms. Then we use distributional similarity and apply word embeddings to capture similarities and the inheritance property, the inherited properties basically. And finally, we measure context specificity as an indicator for the asymmetry in the hyperenemy relation, and basically use it to determine the directionality in a specific hyperenemy pairs. Okay, for the linguistic preprocessing, our goal is to encode and keep a maximum of the linguistic structure in our data, because obviously we can understand that hyperonyms and hyponyms, they're similar not only semantically but also syntactically, and this is why it's very important to keep also the syntactic information in our data. So we apply POS tagging, then we apply dependency parsing, and also chunking of collocations and multi-word expressions, because as we have seen, basically multi-word expressions are actually often hyponyms or hyperonyms in themselves. And below you can see a very small example for the pre-processing that we do. Good. Then the second step, so this is where the actual linguistic processing starts, rule-based bootstrapping. Here we made a quite interesting, although not completely unexpected observation, which is that the expression of hyponyms changes over the lifetime of a concept. So when a new concept is introduced, it tends to co-occur with its hyperonym. Why is that? Well, obviously the writer or the author needs some way to introduce and to explain the concept, and it turns out that a very natural way to introduce a concept is actually to refer to its superclass. And then as the concept becomes established, the frequency of co-occurrence decreases in the data. So let's look at an example. The example of cryptojacking, which is a cyber attack. So you already see, very naturally, I know that maybe not everyone knows what cryptojacking is. So I will say that cryptojacking is a kind of a cyber attack, which started in Q4 2017 as the malicious use of a person's computing power to mine cryptocurrencies without consent of the owner. In the chart below, you can see how the usage of cryptojacking evolved over something like 1.5 years, basically. So you can see the gray area, which shows the proportion of those instances where cryptojacking does co-occur with cyber attack, so with its hyponym, and the red area is correspondingly are the instances where it does not co-occur. And as you can see very nicely, the number of co-occurrences diminishes over time because the concept becomes more familiar to readers and there is no need to explain it every time anymore. And in the blue line, so the blue line denotes the average distance in words between the hyperonym and the hyponym for those instances where there actually is this co-occurrence, and you can see that the distance is growing, which means that basically the association becomes more and more loose also in the data. Okay, so how do we do rule-based bootstrapping? From the technical perspective, there is a very well-known approach by Hurst, actually developed already in the 90s, but the nice thing is that it's always kind of reinvented also in recent papers. So in 2018 and 2019, that was actually the basis for the state-of-the-art work on the task. So Hurst formulated something like 70 patterns of these forms x such as y and other x and so on, which can naturally be nicely used to extract potential hyperonymy candidates. That's one thing, and the other thing is also entailment in nominal collocations. So you often have collocations consisting of basically, which are basically denote the hyponym, which then entail their nominal head, which is also the hyperonym of the whole construction. So for instance, you can have security breach, which does entail that there is a breach. And in many cases, we also have basically the hyponym, which even without referring explicitly to the hyperonym, does entail the hyperonym. So things like denial of service, it automatically will entail that there was an attack, basically. Okay. So this was for the pattern-based bootstrapping, which can be used to extract candidate hyperonymy pairs, especially at the beginning of the process, and especially for those concepts that are quite new in the data. Then the next step is using distributional similarity, and as I said, distributional similarity does underlie word-to-vec embeddings and continuous representations of words in the vector space, and this is something that we use to capture also the functional similarity between the items. Note that we use dependency-based word-to-vec embeddings, which also include the syntactic information, because as said, the similarity between hyponyms and hyperonyms is not only semantic, so it's not only like, let's say, topical in nature, but there is also a lot of syntactic and functional similarity involved. So let's look at this chart. This chart was created, basically shows the nearest neighbors for attack. And you can see, so attack is in the top left corner. And you can see that it does capture a lot of hyponyms, signaled by the red marks. And it also does capture a lot of the instances of attacks, such as WannaCry, Stuxnet, Petya, and so on. So this is already, the recall is already quite good, even from a manual perspective. So this kind of chart is actually very helpful for constructing ontologies. Obviously, the less optimal thing that we see here is that it also does capture other concepts which are in no way in a hyperenemy relation with attack. So it does capture synonyms like cyber attack and so on, and it also captures other unrelated terms like attacker, exploit, cyber criminal, and so on. So it does produce very focused domain knowledge, but it doesn't produce any kind of differentiation between hyponyms on the one hand and hyperonyms and other semantic relations on the other hand. But still, obviously, this kind of chart, as said, is very helpful for constructing ontologies and then also maintaining and editing the ontologies in the first place. Okay, so how then do we kind of narrow down this representation that we got from word embeddings to hyperenemy? We do this, as said, by including this additional logical property of hyperenemy, which is asymmetry. So we use context specificity and observe that hyperonyms are semantically more general than their hyponyms. So they also tend to occur in more general, that's less informative contexts. And as many of you might know, basically context entropy is the classical measure for specificity, because it kind of measures the amount of information that's contained in a word or a context. So we use a measure here, which is called SLQS, and which allows us to measure context specificity to determine the directionality in a specific candidate hyperenemy pair. How does it do it? Well, first, for a given context, so for any given context, basically of a hyperonym or a hyponym, we measure the entropy of this context, and then we generalize to the term itself by computing the median of the entropies of all of its concepts, of all of its contexts. And finally, we find out what is the ratio, so the generality of the candidate hyperonym when compared to the generality of the candidate hyponym. And when the generality of the candidate hyperonym is higher, then we follow that there is a very high probability that it's basically the hyperonym. So this is a way just to, when we have a candidate pair of hyperonym and hyponym, then this kind of specificity measure basically allows us to and indicates the directionality in the specific hyperonymy pair. Good. To sum up, I presented a hybrid approach to hyperenemy discovery, which benefits from the various lexical and linguistic characteristics of hyperenemy. So we have a rule-based step in the first phase, which uses lexicosyntactic patterns for bootstrapping. Then we continue by finding out the distributional similarity relations for capturing the nearest neighbors of hyperonyms and their co-hyponyms. And finally, we use an entropy-based approach to determine the directionality based on context specificity. We have seen very nicely that this also aligns with this empirical evolution of new hyponyms in time. Which are captured by patterns due to the frequent co-occurrences with their hyperonyms. And finally, for the challenges and the future work, as I said, this is so far like it's a very pragmatic and empirical approach. So we don't really have a very sound evaluation strategy, and especially an evaluation strategy which would also account for the dynamics and the regular changes in our data. And this would be a major item or to-do item basically for the future. And also we are now studying some ways to manipulate and to structure the vector space which would be indicative of hyperenemy, so which would basically allow us to manipulate the vector space in a way which allows to identify these hyperenemy relations in a more distinct and succinct way. And this is something that has also been taken up in the literature in the past 2 years. So we really hope that we can then also improve the algorithm based on these new findings. I think that's all for today. So thanks to everybody. Please don't hesitate to get back to me if you have any suggestions and feedback on this talk. And obviously, I'm also looking forward to both written and oral questions. Thank you.